I'm Brandon. I've been doing this stuff at Owen Labs for like 7 years now. It's been a while. I started as an engineer, did a bunch of stuff. Now I'm the CEO. Okay, so we are really excited for this new. Am I blocking the stage? For this like new internet that a lot of people in the ZK, MPC, FHE space are contributing to, where developers can use programmable cryptography to create more powerful applications. And we think a key component of this new internet is Mina. Why? Because Mina is super decentralized by design. The way it works is it's an L1 blockchain, but instead of storing blocks over time, we store a proof that there was a blockchain, and we extend that with another proof over and over and over again. So we have you can think like, if I take a picture with a Polaroid camera, one of those cameras where we can like print out a photo. I can like take a picture of you, give you that picture, take a picture again, and now I have like a picture of a picture, give that to you, take another picture, I have like a picture of a picture of a picture, and we just keep doing that over and over and over again, and that's kind of what Mina's doing under the hood. Why is this decentralized? Because, well, we've done a lot of things to make it decentralized, but in particular, this part, you can kind of work with the network, connect to the network with just a little bit of state. So I want to talk about like ZK rollups, because this is kind of like a ZK rollup. So a ZK rollup, for those that don't know, typically you take a bunch of transactions, you roll them up into a proof, and then the proof goes back to a layer 1. What Mina does is it takes a bunch of transactions, makes them into a proof, and then it rolls this transaction proof into that like picture of a picture of a picture, the block proofs, and what we're left with is one single proof. And actually, we launched our mainnet in 2021 before any of the other ZK rollups came out. So we invented ZK rollups. Okay, we call this property succinctness. So Mina is the first succinct blockchain. It's still the only succinct blockchain where not only are the transactions rolled up, but all the blocks are rolled up. And this is cool. It lets you do, I guess this is a toy, but it's cool. In Bangkok, there was a smart fridge in like someone's apartment, and we got a Mina full node running on it. So obviously this is like a joke, but what it shows you is you really don't need large hardware requirements to connect to a node, to connect to the network. And what this can translate to is when users are interacting with applications in Web3, they don't have to connect to a centralized RPC service. They can bypass that and connect directly to the network. So it's just like getting more decentralized. So Mina, we've been working on it for a while. Initially, our release just had normal transactions, payments, stake delegations, things like that. But recently, this year, we just launched an upgrade to enable applications. There's this notion of thinking about applications in Web3 as being replicated. So when you're executing a smart contract on Ethereum, let's say, every single node in the network runs every single line of code right now, and any new node that joins has to re-execute every line of code. And that's just not scalable. So ZK lets us bypass that, and with Mina in particular, we can run something once, particularly off-chain most of the time. We get privacy, we get all these benefits, but most importantly, we only have to execute the code one time. That's like really important for scalability. So, and Vitalik talks about this as like the future of Ethereum. The future of the Ethereum is Mina right now. So we took this base system and said, okay, inside a transaction, we can have a ZK app, a ZK application. And within the ZK app, we can also have a bunch of proofs that roll up. So all of this like rolling up technology, this recursive proofs, we give that to developers. There's an SDK called O1JS, and I really recommend you check it out. But what this does is it leads to a proof singularity. So everything that ever happens, that's ever verified on Mina, gets stored into this tiny proof. And that means any application that's ever run is sort of collected and remembered forever, and anything that's ever bridged into Mina is collected forever into this one tiny proof, into this little singularity. And this is something that we think is like really, really interesting, really exciting. You can do a lot of stuff with it. Today, I want to talk about one thing that you can do with it that we've just started talking about and that we've just started digging into. Sorry, single proof of everything that's ever happened. Great, okay. So there's a new thing that we realized we could do. We're calling Project Untitled right now because we didn't think of a name. So yes, let me motivate the problem here. If I'm like building software on my computer, like Web 2 software, normal stuff, I can just say like, hey, I want to allocate like 2 gigabytes of space on my hard drive to use as application state, and I want to change it all the time, anytime users interact with stuff. And it's an important building block for applications, for like anything interesting. In Web 3, this doesn't really exist. So we there's this trilemma that happens. People love trilemmas in crypto. So you draw a triangle. So this trilemma here is there's no like storage solution, state solution that's cheap, decentralized, and lets you update it cheaply. So if you have cheap storage costs and cheap updates, then you have like AWS, Firebase, Google Cloud, that kind of stuff. If you have low storage costs and decentralization, then you get like existing Web3 services, but you can't update the data. And if you have high decentralization and updates, you can do things on chain, like that works, but it's too expensive to store a lot of data. So Project Untitled is in the middle. And you might be thinking, like, what the hell does this have to do with all the other stuff we were talking about? Well, I didn't tell you how it works. Yeah? So how does it work? It's powered by a polynomial commitment scheme. And this is probably something that people haven't heard of before, unless you're like super deep in ZK. Okay, so what's a polynomial? It's like this thing, ax plus b equals 0, or like ax squared plus bx plus c, right? From school. Okay. So that's a polynomial. What's a commitment scheme? I'll talk about like a vector commitment scheme. So what that means is like I have a bunch of things in order, and I can commit to them. That's that C. And this commitment is like very small. And this commitment, it's hiding. So it means that if I just see the commitment, I can't see the data. And it's binding. That means that if I pick C and I show you C, then later I can open it. I can give an opening proof and then show you the D1, D2, D3, D4. And you can recompute C and be convinced that at the time I showed you C, I already had this data. So this is like a general thing, the vector commitment, and there's something that like maybe a lot of you have seen, which is a Merkle tree, or at least you've heard about. So a Merkle tree is a type of vector commitment. You have a bunch of data, and the way it works is you hash the data, like in a tree, and then you hash the hashes, and you keep going for as much as you want, and then at the very top, what we call the Merkle root, this is the commitment, the vector commitment. And this is useful for a lot of things, and people use it. However, there's something called a polynomial commitment, where you take all the data, you stick it in a polynomial, and then you do a bunch of other math that I'm not going to show, and you can get a commitment out. And the cool thing is, if you pick your polynomial commitment carefully, it turns out if you use the polynomial commitment that's built into all of the ZK stuff that Mina does, you get something that's super nice for storage. So what do you get? This commitment is really cheap to produce. We think it's actually faster than Merkle trees, which is cool. There's a little demo that I can run on my laptop. I have a MacBook Air. It takes 2 seconds to do the initial, some constant setup, and then it's 500 milliseconds per gigabyte extra to produce this commitment for a gigabyte of data, and that's on my laptop. So, I'm excited to run this on a beefier machine and see how much we can scale it. And then there's some nice properties of the particular polynomial commitment scheme that we're using that lets us inject a random challenge into the computation, and that lets us create a decentralized protocol. I'll talk about that in a second. And the other thing is another mathematical property that we can make use of is we can get partial data. So we can say any subset of this polynomial, I want to get that, and we can do that cheaply and prove that we've gotten the right data. And when I'm changing the data, when I'm updating, I only have to change some parts of it. I only need to create a small amount of information in my diff and push that, and I can prove that change is made. So this is the protocol. I won't talk about all of it, but I think the interesting parts, so Project Untitled, it's a layer 1, another layer 1 blockchain with a proof singularity. Talk about that in a second. There's state replicator nodes. These are the things in the network that are storing the data. And then there's an application. And the application is on this side, and it's on this side. And it's an application that can live on Ethereum or wherever. So the settlement layer, Ethereum or Mina or something. And then you can connect that to Project Untitled. OK. So the interesting part here is periodically over time, the network will be producing randomness because it's running and things are happening, and it will basically send this randomness out to the network, and all the state replicator nodes have to reprove this computation with that network randomness, and what that does is it forces these nodes to store the data and always be storing the data and always have it available. And because of the nice properties of the polynomial commitment, we have the ability to update it, to update the data. And the network has the ability to know if certain updates have been applied when the next round of these storage proofs happen. And once we have that, we can allocate some space and update it. And an application can ask for data, and everything works, and it's decentralized. I want to kind of bring this back together. So I mentioned this new protocol that we've just started building. It's a layer 1 blockchain. We're actually going to reuse most of the code from Mina. And what we get is another proof singularity for mutable application state. What's cool about this, beyond all the interesting decentralization things, is this can be easily verified by Mina and by other blockchains. and all that. But there's this nice succinctness property again, right? So the nodes in the network, in this network that are storing data, they want to use their hard drive space to store state because they're getting paid for it that users want. They want to store the application data. They don't want to store information about the blockchain. Typically, blockchains, they grow forever. They get really big over time, right? But when you have a succinct blockchain, when you have a proof singularity, it's really small forever. And that small state means that these nodes in the network can use all of their hard drive to earn money earn tokens and rewards. So, yes. I'm Brandon, O1 Labs. We make Mina, we make Project Untitled. We just started a Telegram group and a Twitter account. We're really excited for this. I guess just one thing I forgot to mention. Why did we even come up with this? So Mina's new update just came out this year, and we've been working with developers, and every single, I shouldn't say every single one, but so many developers have come to us and said, hey, how do I deal with state? I want to have application state. I need to store a lot of it. It needs to be decentralized. Like I'm in Web3 because I want to build decentralized applications. What do I do? And there wasn't a good answer. So we figured this out, and we realized it's not just a problem for Mina developers, but it's a problem for all Web3 developers. So we're really, really excited to build this and help everyone. So yeah, that's the thing. We can, I blazed through that really fast. So if anyone has questions, I can answer them.
Hi. How does Mina do indexing if there's no it's hard to keep the state transitions over time since it's just like a bunch of proofs after the proof?
Yeah. So the question is, you were mic'd. I don't have to repeat it. Okay. So Mina's layer 1, even though it's all powered by ZK, it's transparent. There's no privacy. This was done intentionally. Applications can use privacy if they want. So yeah, nodes on the network do not have to remember the state. However, it's there. So some people are choosing to remember the information and index to run block explorers, to run software so that people can do their taxes, other annoying things. So yeah, it's as simple as stuff is coming in, you just store it to a database in addition to forgetting it in your main client, and that's how the indexing works.
Just a follow-up on that. How do you trust the people who are selectively remembering?
Yeah. So we have a couple Merkle lists built into Mina. So this is a Merkle tree. A Merkle list is where you just have like some data and a hash and new data and a hash and new data and a hash and new data. And essentially what this lets you do is with a single hash, you can store a single hash on chain, and then later someone can prove to you that a piece of data was present in the past with a small amount of information. So effectively, we have enough Merkle lists so that for people that want to prove the correctness of like, yes, this definitely was there in history, you provide a Merkle list proof alongside giving the archive information. So, and then, yeah, we actually thought a lot about this early on. I guess there's another cool thing, if we go to the fridge, like, okay, so I'm storing stuff in a fridge. Like, I don't even want to have these big proofs of all, like the historical proofs. As I just explained it, you need to send like all information that's happened since the point that you want to get the history. And that's too expensive for a fridge. So the other thing that we do is each individual account has a Merkle list called the receipt chain, which is all the transactions that they have sent. And so that list is actually, there's another list that you can use to do these kinds of historical proofs, where it's only as long as the number of transactions that you've sent from your account. So then it scales and works on fridges and phones and those kinds of things. That was a long answer, but.
Thanks, Brandon. What type of snark does Mina use? Will Project Untitled use the same snark?
Yeah.
It will?
Yes. So Mina uses a proof system called Kimchi that we built. It's a variant of Halo 2. And the kind of the secret sauce is it's super, super good at recursion. Recursive proofs are really fast. This is important for succinctness. And yeah, so by accident, the polynomial commitment scheme that we use happens to be perfect for, this is kind of why we were able to discover this solution. The polynomial commitment scheme that we use is perfect for dealing with storage. So, so we can lift out that polynomial commitment scheme, and it's actually like ZK native. So it plugs really nicely into a succinct blockchain. You can do cool stuff like have ZK authorized updates rather than just like a private key. I have this private key, I can update it. It can be like, this DAO has signed enough things, or there's enough capital in this account to enable an update of the state. Or a time lock on my like HTML asset for my decentralized application. I have a time lock so that it changes only after a certain amount of time, to protect against hacks, things like that. So there's like a lot of cool stuff that we can do.